welcome to our channel of Sciences and Mathematics. I'm Ernest. Today we're going to look at a concept in vector calculus. And the concept of vector calculus is very important in our discussion because it's in this concept that we're going to look into details on how we can be able to apply some of the specific areas we're discussing here in gravitational fields and structural analysis, and probably in some of the control systems. This is one of the areas in which this concept of vector calculus can be able to be applied, and perhaps in topics like electromagnetism and fluid dynamics. So this is one of the areas in which we have to be keen on, since it finds a wide areas of applications in some of the topics that we have already discussed, and the others which we're going to discuss under the broader topic of physics. So in this case, for today, we're going to look at basically the integration of vectors, and of course, we are going to see that other than ways in which we perform the normal operations for integration, vectors also can be able to be treated using this aspect of integration. And we are going to see shortly on how we can be able to achieve that. So without further ado, thank you and welcome. So for today, our topic of discussion is integration vectors. And as I've said, we're going to see that vectors as well obey the normal rules of integration that we normally use. But in our case, we're going to see how we are going to treat the different components of vectors, especially in three-dimensional space. So in this case, we're going to use the illustration for that particular case, or maybe we're going to use examples in order for us to achieve that. Now, for that case, we're going to assume that if for each value of a scalar variable, we can just give a scalar variable u, and then we say that for each value of a scalar variable u, there corresponds a vector au, and we're going to define au as a vector function of a vector function of u. So basically, if for each value of a scalar variable u, there corresponds, or maybe there corresponds a vector au, we're going to have a vector function that is represented as we're going to have a vector function that can be represented as au, and basically we're going to call au a vector function of u. So therefore, this is going to form a vector function of u. So having said that relationship, if therefore we have au as a vector function, in three-dimensional space we can be able to represent the components of au, which are going to be given as au. This is for a1, the I direction. So sorry for that. This is the I direction plus a2 u, the j direction, plus a3 u, the k direction. So these are the specific elements of this particular vector function that we have defined as au, which is basically, as we have said, a scalar variable u. So the three aspects or the three elements of this particular vector can be represented as that one. So therefore, we can be able to define an indefinite integral, just like as the integral of au with respect to u, that is au du, which is going to be given. Now for these components, as we treat the integrals of other functions, we're going to place them there, and then we find the integral of 1 u du plus, this is the I, so the j. This is a continuation of this specific equation, and then the j a2 u du plus k, the integral of a3 u du. So basically, I'm going to go slow on this so that we can just have this connection. So basically, as we have said that for a scalar variable u, there corresponds a vector function au, and therefore we can represent this one in a three-dimensional elements using a for I, j, and k components. Therefore, from this we can be able to define the integral of this specific vector function of u using the I, j, and k components. And as I've illustrated, this direction for the vectors are going to be placed at those specific points. Now, if there exists maybe another function b, which is a vector function of u, such that a vector function au can be represented as d du, b u, just like that. So if there exists a vector function bu such that the vector function au can be represented as a d du of bu, then we can be able to represent an integral function from this maybe equation for the two vectors for au, vector function of u for a and b, using this specific equation. So I'm going to do away with this so that we have the integral, this one, in form of b. So the integral of a u du is equivalent to the integral of d du b u du. So basically this section of this specific integral is equivalent to au. So we can have an integral of this specific function represented as du bu du. So that's an equation that is going to represent that one. So therefore, from a normal integration, we know that this is going to be equivalent to bu plus a constant, which is another vector that is independent from this function, which is a vector function of u b, and therefore it's another vector. So we can be able to represent this one as a c, which is another vector, which is a vector which is independent of this vector function du. So from the normal integrals that we know that there is a c that is representing a constant, and perhaps we can be able to define this one as a constant vector that is independent of that one. Now suppose this is for the indefinite integrals. Now suppose we have a definite integral that has got limits between alpha and beta for the function of u. We can be able to just do away with this. So we can be able to represent that definite integral whereby, as we have said, we have a condition for the limit, which is for the limit u is equals alpha and u is equals beta. We can be able to represent this definite integral as the integral from alpha to beta of this vector function of u du, which is going to be equivalent as a vector from b to in form of a vector function b still, as we had represented it basically in our previous expression or equation, this one du. So this is going to be equal to b u plus c, and this is from alpha to beta. So this is a general representation for the definite integral. Previously we had seen the representation for an indefinite integral. So this, of course, limits can be able to be defined as we already do for the other elementary calculus that we normally perform for other functions. Now we're going to use our examples to try and find out how we can be able to basically do a calculation for this specific integration of vectors by giving an example. Just to do away with this so that we can be able to have a space for this. So I'm going to write an example on the board which we're going to use in order to find out how we can be able to work out integration of vectors. Now suppose we have a function R which is a vector function of u represented as u minus u squared for the I component plus 2u cubed for the j component minus 3k, and we are asked to find a, the integral of ru du, and b, we are asked to find the definite integral from 1 to 2 ru du. So basically for the first one that we have been requested to find, we're going to find the integral, the definite integral for u du from this specific equation. So implying for the I component that just like the one we are done for the general representation, we're going to have the integral of the first part of it, that is u minus u squared du, and then we add j component, the integral. Now for j we have 2u cubed, and remember 2 is just a coefficient, so therefore we can treat it as the way we treat other normal elementary integration operation. So this one we are going to have negative 3k, so the integration of k into 3 du. So this is a general representation for this specific vector function of u, which is r, which can be represented as I've done on the board. So this one is basically going to be this is u squared over 2 for this first part minus u cubed over 3. Now this is for the I component, and then we're going to have plus. Now for j, this is going to be u4 for the coefficient of 2 there, so it's going to be a half. So I just reduce it for the sake of our space. So we have u4 divided by 2, and then we're going to have minus. Now for k, it's going to be basically 3 u. Okay, so this is j. Therefore, if you try to look at this, still we can be able to do further simplification for this, like the first part of the I component, that's like terms. So therefore we can be able to do a simplification for this. And remember, in our case here, we are going to have the first case, which is going to be represented as this, and we can just do a simplification for this and find out the value. And for the second one, whereby we are requested to find the definite integrals, and for this we see that there is a value c, a vector c, that is independent of this other part of the the expression, which is given as c. Now for the definite integral, we're going to do a substitution whereby we're going to just perform a normal operation just like this, but try to do a substitution whereby we're going to include these limits for 1 and 2 in these specific values. So therefore we're going to do a substitution for 2 in our expression, and that is going to give us, for the first one, negative 2 over 3 for I, and then plus 8 j minus 6k. Now, I'm going to show on how we achieved that one so that we cannot be just left hanging. So this is minus, the second one we're going to have a 1 over 6i plus a half j minus 3k. And then lastly, it's going to give us negative 5 over 6i plus 15 over 2j minus 3k. So basically what I've done is that I've done a substitution for this. I've already performed an integration. So we're going to find the LCM for this, which is basically 6. Therefore 3, this is cos here 3 minus cos here 2. So basically this is what has given us, just a minute. We're going to do a substitution for this for 2. This is going to be 4. Let's just do away with it first. This is going to be u squared is going to be 4 over 2, which is going to be 2 minus, this is 2 cubed 8 over 3. So this is 2 over 1 minus 8 over 3 is going to give us negative 2 over 3. That is 6 minus 8 over the common multiple, which is 3. It's going to give us 8. So normally we are going to perform the same operation for substitution for 2 here. This is 16 over 2, it's going to give us 8. And the last one for you, basically for 2, it's going to give us 3 times 2 or 6. So the second part of the equation is as for substitution by 1. And it's going to give us a resulting, maybe a result for that one as is. So basically, for this integration of vectors, we first identify the vector function of our u, which has been given as r, and then for each respective component we just perform a normal integration and then maybe do a substitution in order to find the values of these specific parts for definite integrals, and then this is going to give us the answer. But remember, for the indefinite integrals, we say that there is a vector that is independent of other parts of the function. So we're going to begin in order to ensure that we have already represented it in our expression. So I hope that given maybe a vector function and other apart from the ones that we have illustrated on the board, it will be easier for us to try and figure out how we will be able to calculate its integral. So I hope that is going to assist us, of course, do the applications in electromagnetic field and other areas that we have discussed. And then it's going also to be maybe applicable in some of the relevant examples and other problem solving techniques that we're going to apply in our discussions. So I hope that it will assist us in trying to attain those objectives. And I hope that this among discussions is going to complement on the concept of vector calculus. So thank you. Bye guys. God bless you.